So in a sense, we are finished, and so it's just practice from now on. And so I thought I would start that by talking about kind of the most complicated and general problems, at least some of them, that go under the name of dynamics because something's changing with time. And this has just really two basic ideas, and you use those ideas over and over and over. But the two basic ideas are that if you want to change the velocity of something, you need a net force. And if you want to change the angular velocity, you need a net torque. And so I thought I would just throw up some problems that have those kinds of ideas that you have to deal with. And so here we go with one of the more complicated ones. This is a solid cylinder. You're seeing the round end of a cylinder. You're looking down the cylinder axis. Radius 2r. It's sitting here, and it's got what it says is a yoke with a frictionless axle and then a string tied to it. So it's a cylinder that looks like that. They've hooked it up so that there's a string tied to it, and it can roll along this thing. And so it rolls. In other words, it rotates clockwise and moves to the right when this thing is released. So the mass here falls, this thing rolls to the right, and this string, or this wire, whatever it is, the string is hooked over a pulley. So you have three objects. If you just look at them, you say, okay, there's three objects that are moving. This mass falls down. This pulley rotates clockwise. This complicated thing back here, the cylinder, does two things. It moves to the right, and it rotates clockwise. Because there's two kinds of motion for that cylinder, we're going to need to write this equation twice. Because there's only one kind of motion for this mass, we'll need to write, and it's translational motion. It's the movement of the mass through space, not anything rotational. We'll just need one equation, that first equation, F equals ma. And because this pulley only has rotational motion, we'll need an equation for that, for the rotational motion. So if you look at that, you say, well, there's three pieces. They're all moving. In fact, they're all accelerating. You can guess that they're all accelerating because they've told us that these are all a bunch of frictionless things. So this rotates around this axle without friction. The cylinder rotates without friction. This pulley rotates without friction. So I hate to say without friction. I would always say, and I tend to say, with negligible friction. You do the best you can, and if the best you can is not good enough to account for the motion of this, then you'll have to add in the fact that there is friction. But probably it's small enough that you can figure out the motion of this thing reasonably well. You can usually make friction forces fairly small. Just depends on how hard you're willing to try. And the only other possibility for friction is on this surface between the cylinder and the tabletop. It says that the cylinder rolls without slipping. And so that tells you something. First of all, that tells you that there's a friction force between the cylinder and the table. Because the only thing, if this thing gets pulled to the right, the only thing that's going to start it rotating is that friction force. I'll get to that in a second, but that's one of the things you can conclude from this. but also because it doesn't slip. That friction force as it applied to this thing, because it doesn't slip, because it isn't kinetic friction, there's not going to be an energy loss. I don't lose energy because of static friction of one hand on another. I lose energy when my hands actually slide against each other, and then I can heat them up. And so nothing here is sliding. The axles don't have friction. So even though the things that are rotating against an axle, and so in some sense they're sliding on it. They're sliding on that axle friction-free. So the fact that that everything is friction-free enough that we don't lose energy that way by friction forces tells us that as this thing falls and you lose gravitational potential energy, an energy has to go up. You're going to gain kinetic energy. As this thing falls farther and farther, you're going to gain more and more kinetic energy. That just tells you that this thing's going to be accelerating. There's no way it can fall at a constant speed, lose gravitational potential energy, unless that energy was going somewhere. And there's no friction forces to do work, so there's no way to dissipate energy. So all the gravitational potential energy this loses has to go into kinetic energy, and so things are moving faster and faster and faster. So just that picture of it tells you that things are going to be accelerating. Also, the problem says, find the acceleration. So that's a hint right there that this thing is accelerating, but you could have figured it out for yourself without doing any calculations, but just thinking about energy loss. How do you do calculations for these things? Well, you have three objects. Let's do the pulley first. The reason I want to do the pulley first is that it tells you something really important. There's a tension force by the string. And I'm going to say by the vertical string. Because there's another tension force. The string loops around. It's back here too. Since I called one of them a vertical string, I should call the other one the horizontal string. They're the same string. But as long as that string has a friction, so here's another friction force. As long as that string has a friction force with the pulley, then as the string moves, the pulley will move. As long as that string is not slipping on the pulley. If it's slipping on the pulley, well, suddenly there would be another possible energy loss and that I hadn't talked about, so I wouldn't know for sure that it was accelerating. But I'm sure it says the string doesn't slip over the pulley surface. In other words, the string just rotates the pulley. So the pulley has an angular acceleration. How are you going to get an angular acceleration of the pulley? It starts not moving, and then it picks up speed. How are you going to get an angular acceleration? And you can tell when this thing falls that it's going to be a clockwise acceleration. And the only way to do that is if the tension by the vertical string is bigger than the tension by the horizontal string. The tension in the string changes at the pulley. This tension is larger so that the sum of the torques, what do you have? You have a clockwise torque tension by vertical string times the radius of the pulley, that's this R right here, is a clockwise torque minus tension by horizontal string times r is a counterclockwise torque. This tension by the horizontal string is trying to rotate it counterclockwise. This tension by the vertical string is larger, so the clockwise torque is bigger. And the sum of those two, I put a minus sign in between because one is clockwise and one's counterclockwise. The sum of those two is going to be, just by this equation here, I of the pulley, the rotational inertia of the pulley. Yeah?
Isn't it like friction though, not tension, that's what's causing the pulley to rotate?
It is a friction force, basically. But the problem is that friction force acts over the whole radius, over the whole place where the pulley is touching. And you don't exactly know how much of the friction force is at what part of the pulley. All you know is there's a tension force down here and a tension force on that side, and you don't know the details of what the pulley and string interaction really is. It is a friction force. The reason the string pulls on the pulley harder on this side than that side is because of friction force. But the difference between those two tells you what the friction force is, basically. The difference between those two is a measure of the friction force. The problem with the friction force is you don't know how big it is at any particular point. You just know that the difference between those two is that friction force. But you're right. I mean, it's another way of saying it is the reason this tension is larger, the vertical tension is larger than the horizontal, is that this pulley is pulling counterclockwise on the string. If the pulley pulls counterclockwise on the string, then by Newton's third law, the string is pulling clockwise on the pulley. The string, that friction force by the string is rotating the pulley. The reason I can take the difference between those two is because of, by Newton's third law, the difference between those two is just the friction force backwards by the pulley on the string. So then this gives you an equation for the angular acceleration of the pulley. One of the equations that you need